We're going to talk about collisions and explosions today and how they relate to momentum, conservation of momentum. So take good notes, and here we go. Let's review a little bit. Last time we talked about under what circumstances momentum is conserved. And we'll start off with the just the review with the idea that the net force times time equals the change in momentum of an object. This is the impulse momentum theorem. That's kind of where we started, or where we left off last time. And it said this is the impulse. If you apply an impulse to an object, that will be equal to the change in momentum of an object. But if there is no net force, if the net force equals 0, well, then the change in momentum has to equal 0. If this is equal to 0, then the change in momentum is equal to 0. And if the change in momentum, well, what is the change in momentum? What is delta P? Well, that's P final, the final momentum of your system, minus the initial momentum of your system. Well, that has to equal 0 if there's no net force on your system. Well, what does that mean? Well, add the initial momentum to both sides, and we can say that the final momentum equals the initial momentum. This is conservation of momentum. If there is no net force on your system, then the final momentum of your system will be equal to the initial momentum of your system. So now we're going to apply that to a collision. And we kind of did this last time. If we have object 1 can be a proton, object 1 can be a baseball, object 1 can be a planet or a galaxy. It works at every scale in the universe. And it's moving. Shoosh. You can tell it's moving. And maybe here's object 2. And they're going to collide. Now, a collision in physics means that two objects are going to come together, they're going to interact in some way, and then they're either going to stick together or they're going to fly apart. That's a collision in physics. Like two galaxies can collide. Now, none of the stars actually collide, but the two galaxies can, and their interaction, the force of interaction in that collision is the force of gravity. Okay, or you can have, this could be the cue ball, and this could be the 8 ball and pool. Okay, so but all of this works the same way, because this is before. Okay, before the collision, and let's just put them on these are pool balls, and they're on a table. Let's see, during the collision. So now ball 1 is in contact with ball 2, and they are applying equal and opposite forces to each other. So this is the force on object 1, but that's going to be equal but in the opposite direction of the force on 2. All right. This is Newton's third law. This is the force that ball 2 applies to ball 1. This is the force that ball 1 applies to ball 2. Newton's third law says for every force on one object, there must be an equal and opposite force on another object. So these are equal and opposite forces, and they happen for the same amount of time. Now, what I'm going to do is I'm going to define this to be my system. In other words, I'm just going to look at these two objects and the forces that are acting on them. Now, there are outside forces acting, but there are no net outside forces acting, right? Gravity is pulling these pool balls down, but the normal force is supporting that, and the normal force and the force of gravity are canceling each other out. right? But this force and this force, they're equal and opposite also. So when I look at my whole system, what's the net force on that entire system? 0. There is no net force on this system. If I take these two billiard balls and say that they are my system. No. What if instead I said, no, you know what? Object 1 is my system. Just ball 1. That's my system. Is there a net force on this system during the collision? Yes. Ball 2 is applying a force to ball 1. So if ball 1 is my system, then there is a net force on it, and it gets its momentum changed. Its momentum is not conserved. Its momentum is changed from the impulse provided by ball 2. If ball 2 is my system, I'm just going to look at ball 2. It gets its momentum changed. So there is a net force on ball 2. So its momentum gets changed by this impulse right here. But if they're both in my system, then these two forces cancel out, in that the initial momentum of my system is going to be equal to the final momentum in my system. And so now we have this concept during a collision where momentum is conserved. That is, the change in momentum of ball 1 is equal but in the opposite direction of the change in momentum of ball 2. So both balls get their momentums changed, but those changes are equal to each other but in the opposite direction, so that when you add them up, you get 0. Now, what does this mean? And we did this last time. This means that the initial momentum of my system will be equal to the final momentum of the system. Now, here's one thing you have to know. When I write this equation right here, this is the total momentum of the entire system before the collision. This is the momentum of my entire system, which is both balls here, after the collision. So they include both things. And so I can say, well, if I have these two, maybe, by the way, let's just say ball 2 isn't at rest, but maybe they're moving together like this, and then they interact, and then they fly apart. Well, this means that I can do this. If you have a collision, thank you. You can say M1 V1 initial plus M2 V2 initial. This is the momentum of ball 1 before the collision. This is the momentum of ball 2 before the collision. That's going to be equal to the M1 V1 final plus M2 V2 final. So if you get a collision between two objects, and that's all I'm going to do. I'm going to give you two objects that are going to collide. This is where you start. In a collision, the momentum is conserved just before and just after the collision. The momentum is conserved. You can take this initial momentum and expand it out into object 1 and object 2. Now, what if object 2 wasn't moving? What if V2 initial is 0? Well, this term just goes away. And you have M1 V1 initial. That's all the momentum in your system. Okay? But if they're both moving, you got to do this. Also, make sure that you understand that these are vectors. So if I give you a velocity of 2 meters per second here, this is positive. But if this one's moving this way, let's say at 3 meters per second, to the left, you got to make it negative in your equation. So make sure you do that. because I'm not going to have time today to do any example problems. So this is how you start a collision problem. All collision problems start like this. Now there's two kinds of collisions that we're going to talk about, and then we'll talk about explosions. Let's first talk about inelastic collisions. In an inelastic collision, we lose kinetic energy, or mechanical energy is lost in your system just before and just after the collision. Where does it go? Where does the energy go? It gets dispersed into the environment. Now, almost all collisions that you see on a day-to-day basis are inelastic collisions. You're going to lose some of the kinetic energy. Okay, when you crash your car into a pole or whatever, we're losing the kinetic energy. And anytime, like if you see two things crashing, they come together and you just, and then maybe they bounce apart and pieces are flying or whatever. But if you're hearing sound, you've lost kinetic energy. By the way, next time you're in a head-on collision, here's what I want you to do. When you're in a head-on collision, hopefully the airbags deploy, so you walk out of your car, and then in the crumpled up hood of your car, feel the metal, in the crumpled up metal. You got to do it really quick, but feel it. It's a little bit warmer, because bending metal, plastic deformation where the metal crumples together but stays crumpled, doesn't spring back, it's going to be a little bit warmer. Yeah, so you can feel the loss of kinetic energy in an inelastic collision. In an inelastic collision, here's what we're going to do. We're going to say that the initial momentum is equal to the final momentum. This is true for all collisions, including inelastic collisions. But the initial kinetic energy is greater than the final kinetic energy of your system, because we lose it. And where does that delta K go? Delta K, this means delta K is negative, and we basically disperse energy is dispersed into the internal energy of the environment. Oh, and also the objects themselves, they can be vibrating and they can be heated up a little bit. You can raise the temperature of them a little bit, as well as the environment. But you're going to lose kinetic. Now you have these other kind of collisions, and these are called elastic collisions. Now, in the everyday world, there are very, very few elastic collisions that are truly elastic. But some of them are so close to being elastic, they're a little bit inelastic, but they're so close to being elastic that we can model them as elastic collisions. And we're gonna do that next week when we play with those cars with little springs in them. But in an elastic collision, the initial momentum is equal to the final momentum. Notice that momentum is conserved in all collisions. If you look at something just before the collision and just after, there's no other net forces acting on your system, then momentum is conserved. But also, the final kinetic energy will be equal to your initial kinetic energy. You don't lose any kinetic energy. So that's what defines a inelastic collision. Inelastic collisions are really hard. This has an additional equation. Like, okay, let me rewrite. This is M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Okay, but in here, you also have 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared equals 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Oh my gosh, went off screen. Try solving these two equations simultaneously. I'll give you a medal. Algebraically, these can be difficult, but you can start here, and chances are, like, one of the initial velocities will be 0, and you can use these to solve problems. You can use both of these to solve problems. Now, finally, we have these things that are called explosions. This really isn't in your book, I don't think. They don't really define it, but I'm going to do it anyway because they're cool. When you have an explosion, here's a real simple explosion. Suppose I've got a car like this, a little cart. You're not going to think of this as an explosion, but it is. And it's tied by a little string to another little cart. And they're at rest. But I have between them a crushed in compressed spring. So, but the spring isn't allowed to push them apart because the string is there. Well, what if I cut the string? What's going to happen after I cut that string? Well, you're going to get a force pushing car 2 this way and a force pushing car 1 this way. And these forces are equal and opposite. For every force on one object, there's an equal and opposite force on another object. They happen at the same time. So all of that same reasoning that I used before is going to be there, which leads us to the conclusion that the initial momentum is going to be equal to the final momentum. But how much kinetic energy did these cars have before I released the spring? Well, 0. Because they're not moving. But if I cut the string, what happens to the pieces? Well, car 2 goes that way and car 2 goes that way, or car 1 goes this way. So now these cars have kinetic energy. They didn't have any kinetic energy before I cut the string, but I cut the string and the spring pushes them apart, and now they've got kinetic energy, which means that in an explosion, the initial kinetic energy will be less than the final kinetic energy. And if you've got more kinetic energy than you started with, that means there had to be some internal source of energy. There had to be some energy stored in your system that pushed the objects apart and gave them kinetic energy. Now, of course, the most extreme version of this is a bomb, or let's say you have a hand grenade and it's just sitting on the floor or something. It has no kinetic energy, but there are chemicals inside it that react very quickly and turn into a gas very quickly and expand very quickly and apply very, very high forces to the outside container of that hand grenade, and it pushes all those pieces in all directions and gives them kinetic energy. So you've got, right after the explosion, you've got a lot more kinetic energy than you started with. So the difference between elastic collisions, or inelastic collisions, elastic collisions, and explosions is what's going on with kinetic energy. In inelastic collisions, you're losing kinetic energy. In elastic collisions, you're conserving kinetic energy, And in explosions, you're gaining kinetic energy. Okay? But in all three types of interactions between two objects, momentum is conserved. One last thing. One of the things I ask you to do in the problems is figure out how much kinetic energy was lost, particularly in inelastic collisions. And the energy lost is, the percentage of energy lost is the change in kinetic energy over the initial kinetic energy. Multiply that by 100% and you get a percentage lost. So just go K final minus K initial. That'll be a negative value. Divide it by how much energy you started with, and that's the fraction of energy that you lost. If they ask for a percentage, you multiply that by 100% and you get a percentage lost. This is the kinetic energy lost. This is the kinetic energy you started with, so you can figure that out that way. Okay, now the main thing you got to do now is use these basic ideas and basic equations on a lot of little problems. So I gave you some example problems to work in from the book. So do those, given, find, and solve, draw pictures, all that sort of thing. And then I gave you those supplementary problems. So do the same thing for that. Any questions? Okay. That is all.